AC voltage controllers, a circuit in which a thyristor switching circuit is placed in between AC supply and the load to control the power flow by varying RMS AC applied voltage to the load is called AC voltage controller. Here, a fixed AC is converted to variable AC, and applications are speed control price, lighting control, heating, etc. This is our AC voltage control circuit where AC supply and the load. In between these two, we have a thyristor switching circuit which is going to control the input supply which is given to the load. Now this is again two types. That is first one, on-off control, and second type, phase angle control. In on-off control, thyristor switches connects to the load to the AC source for a few cycles of input voltage and disconnected for few cycles. Let it be, this is our AC supply, then turned on for few cycles, cycle 1 and cycle 2, then it's turned off and again it's turned on. Let this be n cycles and turned off for n cycles. This is our output, whereas this is our input in on-off control. Whereas in phase control, thyristor switches connects the load to the AC source for a portion of each cycle. This is our input, then our output will be, let this be a cycle, then this is turned on from here to here only. This is off time within the cycle. This type of control is known as phase angle control. Phase angle control again divided into a single phase and three phase. Again this single phase is divided into half and full wave with different loads. Similarly, three phase again divided into half wave and full wave converter. Principle of on-off control. Here we have considered a single phase full wave converter. The thyristor switches connects the supply to the load for a time of Tn, disconnects for the time of T0. This is our input waveform. For n cycles, the thyristor switch T1 and T2 are turned on at zero crossing voltage, and for m cycles, T1, T2 are disconnected, resulting this output waveform. The positive half cycle, the supply Vs is going to flow through the thyristor T1 given the pulse signal at zero crossing, and then T1 will turn on, then the current flows through the load R back to Vs negative, so that the entire input voltage is available at the load. Now in negative half cycle, the supply goes through Vs minus to load R to T2 to Vs plus. Here the thyristor T2 is turned on at the zero crossing of negative voltage by giving gate pulse. This is the T2 gate pulse. Then the entire voltage is available at the load. Turning on the thyristors for two cycles here, or else in general let's say for n cycles, and we are not turning on the thyristors T1 or T2 for one cycle here. By general say that is n cycles. Then again we are turning on the thyristors. So we have 1, 2, 3, 4 cycles entirely. Total cycles are 4 cycles we have. We are turning on the thyristors for 3 cycles and turning on the thyristor for 1 cycle. This is N and this is M. And this type of control is applied in the application which have high mechanical inertia and high thermal time constant, like industrial heating and speed control. Due to zero voltage and zero current switching of thyristor, the harmonics generated by switching action are reduced. For our sinusoidal input, that is we have Vs equals to Vm sin omega t equals to root 2 Vs sin omega t. If the input voltage is connected to the load for n cycles and disconnected for n cycles, then the RMS output voltage can be formed, that is V0 equals to n by 2 pi n plus m integral 0 to 2 pi 2 Vs square sin square omega t d omega t, entire thing under the square root. Then if you calculate this, you are going to get Vs square root of n by m plus m. We can write equals to Vs square root of k. This is RMS, where k is the n by m plus n is called duty cycle. So we have some conclusions. The power factor and the output voltage vary with the square root of the duty cycle. The power factor is poor at the low values of the duty cycle k. If t is the time period of the input voltage, then m plus n times t is the period of on-off control. If m plus n of t should be less than the mechanical and thermal time constant of the load and is usually less than 1 second, but not in hours and days. The sum of m and n is generally around 100. And we use the formula, that is power factor equals to square root of n plus n by m plus n equals to root k to determine the power factor with m and n in days. Principle of phase angle control. Here we consider single phase half wave control. We have one thyristor and one diode. So we can control only positive half cycle by varying the firing angle to thyristor T1. A pulse is given to the thyristor T1. Then the input is going to appear across the load in the positive half cycle. Then in the negative half cycle, we have a diode which is going to conduct continuously. So we cannot control the diode. So the input is going to appear across the load. So these are the waveforms for this AC voltage controller. We can control only the positive half cycle and half of the wave, we can say. So this is known as unidirectional controller. Due to the presence of diode, the control range is limited and the effective RMS output voltage can only be varied from 70.7% to 100%. The output voltage and input current are asymmetrical, so contains DC component. Since we have an input transformer, it may cause saturation problem. This single phase half wave AC controller is suitable only for low power resistive loads such as heating and lighting. We have Vs equals to Vm sin omega t, which equals to root 2 times Vs of sin omega t. Input voltage and the delay angles of thyristor T1 is omega t equals to alpha 1. Then the RMS voltage V naught RMS is given by 1 by 2 pi of integral alpha to pi 2 Vs square sin square omega t d omega t plus pi to 2 pi 2 Vs square sin square omega t d omega t, everything under the square root. Vrms equals to 2 Vs square by 4 pi of integral alpha to pi 1 minus cos 2 omega t d omega t plus pi to 2 pi 1 minus cos 2 omega t d omega t under the square root. Then if you solve this, you are going to get V RMS equals to Vs 1 by 2 pi of 2 pi minus alpha plus sine 2 alpha by 2 under the square root. This is our V RMS. Now the average value VDC is given by 1 by 2 pi of integral alpha to pi root 2 Vs sin omega t d omega t plus pi to 2 pi square root of 2 Vs sin omega t d omega t. Now when you solve this, you are going to get VDC equals to root 2 Vs divided by 2 pi cos alpha minus 1. This is our VDC. If alpha is varied from 0 to pi, then V naught will vary from Vs to Vs by root 2 and VDC is going to vary from 0 to minus root 2 Vs by